Can I have your attention, please? People who are standing, please be seated. For next 1 hour, we have a very entertaining, tantalizing session. So people, please do sit. I would use entertaining and tantalizing because when we use these words, people are attentive. Otherwise, the sessions become educational, academic. Thank you, gentlemen, for the kind attention. I am Debashish Bera. I am leading energy and strategy consulting business for APAC businesses. Had been in the firm for more than 6 years, overall experience 22 years in oil and gas. Accenture has been a global management consulting firm doing businesses across, if you name any oil and gas clients, Accenture has been providing service to them. So it's been a great privilege to moderate such a session with my esteemed panelists who are industry honkos. The audience I can see filled of attention, spending years in this industry trying to make some transformational move in AI, ML, digital twin, etc. So with this, we start the session and we have speakers from public sector, private sector, and industrial software manufacturer and automation leader. Let me introduce the speakers one by one. From Indian Oil, we have Faridul Kader and Prabhas Jha. Faridul has been there in Indian Oil for around more than 16 years, working in automation, AI, ML stuff, refinery planning, optimization, coordination. He and his colleague Prabhas Jha, who is also 16 years chemical engineer, MBA, part of the planning and coordination team as a senior manager, have been working there in the planning department doing refinery AI ML stuff there. Great to hear from their perspective what is AI ML meant for a refinery. That's one perspective. Second is we have Ravindra Aglave, who is director process Siemens digital industry software lead, and he has came all the way from Houston to share his experiences. It would be great to hear his perspective, his company's perspective, how Siemens has grown the software businesses, and it is one of the revenue generating unit for their company. The third presentation we will hear from Mr. Ashok Kumar, who's from GAIL. We'll hear his perspective from the process gas chromatography of gas phase polymerization reactors. And the final presentation will be from Mr. Satya Narayanan Arunachalam, who is the Vice President Technical, more than three decades of experience in this field. Without that, I'd like to introduce Faridul Kader. Please come onto the stage and share your perspective on ML applications for accurate production plan.
So, good evening, everyone. So, coming straight to the topic, I and my friend Mr. Prabhas from Indian Oil Corporation Limited will be presenting our perspective on the machine learning applications for accurate production plan. So, before delving into detail, the objective of this use case is to leverage the historical yields and quality data from critical refinery process units, which are by and large secondary processing units like delayed cokers, DFCCs, the catalytic reformers, to guide LP planners, which is the supply chain planners, in selecting the most appropriate model drivers. This approach aims to enhance model accuracy, uncover key insights, and identify the primary drivers impacting the product yields. So how does the IOCL planning model component look like? The scale of operations of the IOCL supply chain is such that we manage 10 different refinery sites. We have 3 crude pipelines, 26 product pipelines, 20,000 plus kilometers of pipeline coverage, 350 plus primary distribution centers, and 55,000 plus secondary customers, which essentially are the retail outlets. Plus, we have a petrochemical plant, and the overall crude processing is around 85 MMTPA. So such is the scale of operations. So even some percentage accuracy in some improvement in your production plan accuracy can result into huge amount of money. So this presentation is not limited to the supply chain, but a critical component of the supply chain that we have added, which is highlighted on the slide, where we are using AI/ML models in our supply chain for accurately predicting unit yields and selection of important features. What exactly we mean by features? Because in our supply chain planning, our refinery assets are the main source which are supplying the supplies. Supplies are essentially your MS, your diesel, your lube, so on and so forth. From where is this MS, diesel, and all these products are coming from? They're coming from the refinery process units. So until or unless your refinery process units haven't been modeled correctly, or if the nuanced behavior of these refinery process units hasn't been captured in the supply chain planning models, what you end up with is an inaccurate production plan. So what we do in this use case is we complement our existing first principle knowledge with the AI models. We select those drivers which are more important in the refinery process units like catalytic reformers, the FCCs and all, so that on top of the first principles, we use the data models and predict the yields of our secondary processing units more accurately, and thus resulting in a more accurate production plan. Because on the basis of the production plan, you take a lot of important business decisions. So accuracy of the production plan is very important, is of prime importance in that case, and we are using AI/ML models to correctly predict our yields at the refinery process level, and then aggregate that understanding at the macro level so as to end up with an accurate production plan. So that is what, in a nutshell, what we are doing. So this is the analytics use case modeling and implementation approach. So in any digital transformation project, you ultimately start with technology standardization, you go ahead with data standardization, process standardization, and the hardest part is people standardization. So we started from the scratch, and when we started doing data standardization, we had disparate sources of data. Disparate sources of data essentially means you would be having an ERP data, you would be having a real-time database management data, you would be having your LIMS, which is the lab information management data. So all these data would be lying in silos. So essentially, the job of the first step of digital transformation would be to bring that data into a structured format. So for that, you do your data acquisition, then you do your data processing, your data preparation step, which essentially is the data preparation, what you are doing. Then on top of that, once that is done, you do a lot of feature engineering and feature creation, which means a lot of data might not be readily usable in its raw format. So you had to do a lot of feature creation, feature engineering, and then you do a lot of multi-collinearity checks, which essentially means you have to shorten your data sets in order to extract the maximum information possible, which essentially means that there is a lot of redundant data. Just to give you an example, if you have a recycled gas flowing into your hydrotreaters, now the recycled gas and hydrogen to hydrocarbon ratio, just to give you an example, people who are more familiar with refinery parlance, that these two data might be highly correlated. So in data science parlance, it's a multi-collinearity problem. So you take only one amongst the two so as to make sure that the information captured in your data models is accurate, and at the same time, you are not overly loading your data with redundant data. So you do a lot of multi-collinearity checks, we drop your variables which are linearly dependent, and then you do a lot of hyperparameter tuning for a lot of data models and algorithms that you have selected. You do validation, you do pilot rollouts. If it works well, you move forward. If it doesn't move out, you again go back to the drawing board that whether the feature creation or feature engineering was right, whether the feature selection was right, whether the parameter tuning was right. So you move in the closed loop. But once you get the desired level of accuracy, you move ahead to the business review. You do the use case review with the refinery process engineers. You do it with the LP planners, so that whether the insights coming out from your data models, whether it is complementing the first principle models or not, or it could be the case that it could be an aberration. So you have to have a human check, so you're not 100% automating the insights that are coming out from the data models. It are subject to various checks from the process engineers and the LP planners. And once they give it a go ahead, you integrate them with the refinery network. You use those understanding in the supply chain models, and what you end up with is a model that on top of the first principle supply chain model, you have a data model that is complementing your existing understanding. So these were the various models that we used. These are a lot of ensemble models, boosting, bagging, a lot of techniques that we used to finally come up with the data models among these models, which helped us in selecting the proper algorithms that represented adequate performance for the data set that we had. So to elaborate further on this is an example of a CCRU model that we use. So just a use case of a secondary processing unit model that we used. So we had a DCS data where we had used all the important process parameters. They were 116 in number. We used important predictive parameters of CCRU, namely the C5 plus reformate yield, the net gas yield, the off gas yield, LPG yield, and hydrogen yield. You had a lot of laboratory data, which is the feed naphthenes plus twice of aromatics, which essentially is called the feed index of a reformer feed. Specific gravity. For a PX plant, a paraxylene plant, the C8 aromatic content of the reformate holds a lot of significance. The aromatic content from the reformate, like reformate specific gravity, weight fraction of pure hydrogen. So all these lab parameters were input to our model for training of these models. So but what we got for the prediction accuracy, when we did a lot of feature engineering, the multi-collinearity checks, and what we ended up with after doing this ensemble modeling, the model output was around 98% accurate. So when we tested this data with actual plant performance, the quality prediction was greater than 97% accurate, and the yield prediction was around 98% accurate. The next step that we took was we integrated this model with the refinery network, which is the supply chain models, and the models were validated on the live platform. The user acceptance test happened, and we finally went go live with these models. So as of now, we are incorporating the insights from the data models in our supply chain models. So these were the various methods that we used. Once we used the raw data, we had some level of accuracy. When we did IQR and we did a lot of multi-collinearity checks, we improved upon the accuracy. When we did the IQR, we did the multi-collinearity checks, and finally used the best model, which was the XGB, which is the gradient boost model in this case. We ended with the highest accuracy amongst all the formulations that we tried. So this is just one example that how we went about it and how we selected the proper model. So the workflow and architecture of this overall scheme of things was that in the AI ecosystem, first we did the data ingestion, and how we automated the overall process is through using APIs, because we didn't wanted this process to be a very manual, in the sense that people are taking the dump from the real-time database management system and are feeding to the AI models. So we had a central data lake, and in the central data lake, we had configured all the relevant process tags that were responsible for training these models through the APIs. So we did the data ingestion part. For the data processing, so for model building and deployment, we did the feature engineering pipeline, the training, evaluation, selection, and finally inference model. Now, the main reason why we selected the kind of algorithms that we selected, it was the explainable nature of these algorithms. Because there could be one argument that deep learning is one of the most popular algorithms we didn't use just because of the explainability aspect of deep learning. Because the kind of ensemble techniques that we use for our data set, we found that they used to work well, and the kind of training time that took for these models was within our permissible limits. And finally, in order to see what actually is the output, we had a visualization platform where we are real-time monitoring the performance of these AI models in real time on a dashboard. So how it looks like, so again, the data sources for this AI models, the LIMS, which is the Lab Information Management System, from the planning and scheduling hardware, from the ERP system, from the historian. So we have a plant measurement from the DCS system. It goes into a data historian. Through APIs, we are using these data tags into the AI models. And then we are using yield productions. These are Python-based models. And we are confirming the yields of these models with our existing LP models, as well as the real-time process yields which are actually happening in the field. And once this validation, this two-way validation between the AI prediction with the existing LP plan and with the actual plant is confirmed, we take this input into our supply chain models and onto a visualization platform. So how a visualization platform looks like, it's just a classic example that at Indian Oil, we have n number of CCRUs. Now, just you look at the reformate yield impact on a CCRU. Now, we have two different CCRU at two different locations. But if you look at the CCRU on the above, you are seeing the top feature are debutanizer related features. So most of us who are knowing what CCRU process it looks like is continuous catalytic reforming process, which is responsible for making high octane MS. So high octane reformate comes out of your CCRU. But what this data model is telling us that for this particular refinery, which is on top, probably the reactor and regenerator side of operation works fine. But if you want to increase your reformate yield, the problem lies on the debutanizer side, not more on the reactor or the regenerator side. So if you work on your debutanizer, probably your debutanizer condenser is fouling, probably your debutanizer reboiler is fouling, probably the refluxing that you are maintaining in debutanizer, that is the area of concern for the top CCRU unit. For a bottom CCRU unit, which happens to be from Indian Oil only, here the top features that are impacting the reformate yield are not debutanizer side features, but they are reactor side features. So if you look at the important features that are impacting yield, it is a hydrogen to hydrocarbon ratio. It is a feed N+2A. It has got nothing to do with debutanizer side operations, which was the case in the earlier CCRU. In this CCRU, you have problems on the reactor side of things, not on the debutanizer side of things. So such is the power of the data models that unless or until you don't have this kind of an insight from an AI model, you won't be able to make out that which are my CCRs which are performing well on the reactor and the regenerator side, and which are my CCRs on which I can improve upon the reformate yield if I adjust on the debutanizer or the separation side of things. So this is just one example. There are umpteen number of examples that we have segmented on a case-by-case basis. That if you want to increase a particular yield from one particular refinery asset or one particular refinery secondary processing unit, this is the area that you must be targeting. Like say, for example, for the top unit, you might be targeting on the debutanizer side. For the bottom CCR, you have to target on the reactor side of things. So this is the AI/ML versus actual model performance evaluation. So this is the dashboard that I was referring to. So this is being monitored on a daily basis, and we see that the model performance of the AI/ML model vis-a-vis actual, this is within permissible limits. It's within 1%. So this we are monitoring. If you can see the date, the date stamp on this. So this is for the latest January. So every day this gets updated. So we continuously get a hang of things, that whether my AI model is predicting things correctly vis-a-vis what is actually happening on the ground. So this is the performance evaluation again for a different processing unit. So again, you can see that with the timestamp, we are daily monitoring it. And as and when there is an issue, it is being continuously flagged, and we go for the retraining of the models or we go for another, or we take decisions accordingly as per whatever needs to be done to bring this accuracy level to permissible level. So this is the planning user interface that we go by. So just summarizing the benefits that we have got from this data model approach on top of first principle approach, that we select the correct parameters, we complement our first principle understanding with these data models, we identify the features that impact unit yields and profitability, real-time AI model performance evaluation and retraining planning is done, real-time LP model performance evaluation is done, and retraining planning is done. We enhance the production plan accuracy, and we do better process unit monitoring. So this is all that we had, and this is what we wanted to share. Thank you.
So that was a wonderful, thank you, Mr. Faridul. And he has highly articulated the interactions between AI ML model to improving the quality and yield parameter by more than 97-98%, which is immense. I mean, it's immense benefit to the company. I'm sure Indian Oil is benefiting from the business savings from accurate production planning. So my next speaker is Mr. Ravindra Aglave from Siemens, and he will talk about the physics-based digital twins for energy industry, a precursor to the industrial metaverse. Welcome, Mr.
Namaste everyone, and as they say in my adopted hometown, howdy, which is Houston, Texas. Thank you for the opportunity to speak here. As the title suggests, I'm going to talk about metaverse. So obviously the question arises, what is metaverse? And we will begin with that. So I have 4 parts to my talk. What is industrial metaverse and how do we define it? What are the building blocks for it? What is the role of physics-based digital twin in creating the metaverse? And hopefully there should be time for at least a few examples of how we bring that together. What you'll realize is my talk is targeting really what the future of industry monitoring, construction, design, technology, and so forth is going to be. So this is something that Siemens is working on with many of our partners, which include NVIDIA, Sony, Microsoft, and so forth, right? So let's look at that industrial metaverse. How do we define it? I'm pretty sure you know what this is, right? Mannequins that are showing particular clothes and so forth. You must have seen that for ages now. What it shows you is how a particular piece of clothing would look on a human. So the mannequin looks like a human, but it doesn't behave like a human. And this is the beginning of the metaverse. Right? We say that a virtual or a digital replica of something, a factory or a plant, that not just looks like a factory, but also behaves like a factory. And that's how we go into the topic of industrial metaverse. So what you saw, that example of the mannequin, is the consumer metaverse in some sense, in a limited sense, whereas the enterprise and the industrial metaverse is what is the future, right? And the potential for it to not only generate revenue, but really generate profitability is tremendous. So it is a place where fast engineering decisions are made, leveraging precise, robust data, both real and digital. And throughout this session, as well as the previous sessions, we have seen many examples of that. And some of the keywords in this is visualizing, gaining insights in a realistic environment, which is based on AI and ML, meeting in real time, collaboration of various parts, data, and so forth, and continuously and interactively evaluating, simulating, predicting, and so forth. Right? Those are the essential elements of metaverse. Why is it important? Because it has the potential to really impact many parts of the industry, whether it is material, whether it is energy, whether it is productivity, all of that going towards sustainability. And all the people who are actually taking photographs of the slides, I have a request for you. I'll flash my contact details at the end and I'll send you the slides, so it'll save a lot of time for you. So let us go and look at what are the building blocks of metaverse, right? So we define them at least 4. It does not need to be just 4. Digital twins, real life synchronized models, and you've seen some examples in the previous talks as well, AI enabled systems, and then interoperable platforms. So things that make various platforms collaborate with each other, right? So it is for the purpose of meeting the industry needs in terms of reducing downtime, adapt to supply chain uncertainties, talent, production, customer supply chain, and so forth. And a lot of the technology, actually, you will see that it goes into making a metaverse is already there, right? So AR and VR accessibility, 3D computing power, the last talk in the previous session really talked a lot about it, connectivity and 5G, digital twin and AI. So AI, you saw that in the previous talk as well. And then I think a lot of this was impacted because of the global COVID lockdown, when people really started to think about, hey, if I cannot be present in my plant or a factory in person, how can I do this digitally or remotely, right? And so this is an evolution rather than a revolution. All the way from the 2D designs to 3D designs to 3D simulation, the use of augmented reality, virtual reality, IoT, as well as the use of AI, which is kind of the last stop that you see just after digital twin. All of that is the path that is leading to creation of industrial metaverse. And so it is precise virtual representation of a physical product or a process. It can be used across the life cycle to simulate, to predict, and to optimize. It is made up of multiple representations, not just one representation, right? Could be representation in 3D, could be representation of the logistics, could be representation of the data that was shown in the previous talk about productivity. And it is an evolving object with a life cycle that needs to be managed. It includes closed loop digital twin, which provides for bidirectional connectivity. That means what is happening in digital or virtual interacts with what is happening in real. And the core of this, or the basis of this, is what we, or Siemens calls as executable digital twin. Now, executable or a digital twin concept is also not new. It has been in existence since about 20 years or so. First time it was defined and described by NASA in their space launches about everything that happens on Mars or Moon. You cannot do any experiment, you cannot do any validations, everything had to be modeled. Everything was virtually or digitally, right? And the basis of that is physics-based simulation. Now, physics-based simulation was termed as mechanistic simulation by the last speaker in the previous session. He talked about kinetics, he talked about thermodynamics. In addition to that comes fluid flow, heat transfer, mass transfer, all the physics that defines the behavior. Now, remember what I said at the very beginning. The mannequin looks like a man, but does not behave like a man. And that is the big change that we are seeing. So not only we want a 3D virtual reality that looks like a factory, but we want something that helps us understand how will it behave like a factory. And that behavior can be captured only through physics-based simulation, which is augmented by all the artificial intelligence or machine learning that is today's hot topic, right? So simulation has also been used in the industry for more than 20, 30 decades, 20, 30 years, depending on what type of simulation you're talking about. And it has delivered value significantly, right? Faster scale up, energy efficiency gains. But when it comes to operations, simulation takes longer time than how fast the operations run. And therefore, it needs to be converted in a way that can be utilized at a much faster rate. So on one side, we have historical data, machine learning. You saw many examples, actually, the first talk in this session as well as previous talks. all these models which are based on physics, which are validated so that we have high amount of confidence in that. And now you can use also these models to generate what we call synthetic data. What synthetic data means is information or data about situations or operating conditions for which you don't have any real or measured data, which may not have occurred in the past. And together, both of these create the hybrid models, and they become a lot robust than just relying on one. If you just rely on anything that is coming from simulation, you may not be really having the fidelity that is required. Whereas if you just rely on data that is captured and based on artificial intelligence, it might become unrealistic, and therefore the backing of physics is essential. And so that creates the executable digital twin, and the twin means that there is a exchange between the real and the physical in both ways, right? So virtual sensors was also mentioned in the last talk in the previous session, as well as model predictive control was mentioned, I think, a couple of times in the previous session as well. And this is essentially the core that goes into making the behavior that is necessary to define the industrial metaverse. Now, what does the physics-based digital twin mean, which is the core of the metaverse, right? On one side, you have machine learning. On the other side, you have simulation models. Both of them are essentially data-driven, and kind of a healthy mix of those gives the digital twin. We combine the two fast-evolving worlds today, data-based and model-based approaches. Now, this is a very simple example that we set up in the lab, which is showing you a little crane or a robot. And then the person who is holding the tablet is showing you how the stress on this physical device is in real time, right? It is leveraged by anyone at any point in the life cycle. It is self-contained, which is showing you the behavior of the asset. So the digital twin is not just looking like a crane, but it is behaving like a crane. Now, when we consider all the problems in the refining, chemicals, energy industries, and so forth, there is a whole range of scales that we are talking about, right? So somebody talked about kinetics and thermodynamics earlier, starts from the quantum and molecular scales, goes into thermodynamics, which is the mesoscale, then into continuum, which is your rheology and fluid behavior, the design of equipment, then the plant, and then the entire site. And so we as Siemens essentially provide solutions that can create these physics-based models for all along this chain of length scales. And then there is a hierarchy of how these simulations are. There can be discrete event simulations, there can be manufacturing process and system simulations, and then there can be very detailed processing unit simulations, right? So the discrete event is just a sequence of events, then there is the system level, and then finally you have 3D and multi-physics based models. So you need all of these three aspects or components essentially to complete the physics-based models. Now we have defined what the metaverse is, we have looked at what the building blocks are, and then we have defined what these physics-based digital twins are. So we have a couple of minutes left, and we can look at some of these examples, right? So the 3D and multi-physics based are very, very detailed level. So here is one example. Heat exchangers or any thermal units that you see. For example, tube steam temperatures, flow and thermal simulations can be used, which can be then used to calculate the stress levels, which then gives you a output which you correlate the temperature stress data at key locations. And that correlation can be then converted into a reduced order system model. And this reduced order model essentially calculates things very fast at the runtime. And so the correlation is showing that, you know, what we predict from the reduced model is same as what you get from the detailed model. And then the reduced model gives you a real-time assessment of stress and fatigue. And what that means is that if I am having a sensor that is giving me a temperature data of a stream, immediately I can go and look at what is the stress response of it, and from that estimate what is the fatigue analysis. And then the fatigue analysis tells me in real time what kind of danger do I have because of fatigue that can damage the equipment or any such thing, right? So that becomes a operational temperature data to stress history and update the fatigue in real time. Now you have a system or a factory that is behaving like how it should be, not just looking like what it is, right? The next level I spoke about was system level models. This is an example that comes from a chemical plant in Europe, where a large pipeline, essentially one was curious to know what is the rate of steam injection all through the pipeline. This is an old plant. There are very few sensors, and there is no other way to know how much of steam is flowing through or injected and how to optimize it. So based on the model, what we did was that we could monitor the amount of steam that goes in and optimize the energy efficiency of that, right? So there is a 10% plus reduction in the operating cost just because you could see in real time how much steam is going where in the entire pipe network. And then there are discrete event models. We see to reduce kind of, let's say, robotic programming or any other kind of automation systems that are on a process level. We have tools that can simulate what happens with respect to the machines, but also with respect to the humans that are running and operating inside of a factory, right? So robotic programming times, debugging times, this can be reduced significantly. And then the final element of this is integration. Now we have seen that if you are having models of different kind and you have data assimilated or analyzed of different kind, you also need systems that can integrate them together, right? So diverse systems such as ERP systems, manufacturing and lab systems in order to improve this productivity. So the case actually comes from one of our customers, BASF in Germany, that reduced their deviations, essentially compliance deviations by going paperless and going to a completely digital system, right? So you will see a lot of the names of our solutions. So I will end with just a short video that gives you how this metaverse would look like in future. So this is a video that was created for a battery manufacturing plant, battery being, you know, the future energy storage, and then showing you the monitoring, the equipment. You saw a very 3D image. You see that simulation that is essentially telling you how this particular mixing unit is operating, and then all the walkthrough, robotic elements and so forth. So this is just a conceptual development that is going on. And with that, thank you very much. There is my email and contact address if you want to get these slides from me. Thank you.
So thank you, Mr. Ravindra. This is exciting. So first presentation was all on AI ML stuff in a refinery, and the second presentation is adding some more stuff into that AI ML and getting a metaverse out of it, generating synthetic data, and we can do immense out of that synthetic data. So there is GenAI. We'll not talk about GenAI now. I'm inviting Mr. Ashok Kumar from GAIL to speak about digital twin for process gas chromatograph for gas phase polymerization reactors. Over to you.
Good afternoon, everyone. And thank you, sir, for the introduction. As we have already discussed in previous two sessions that digital twin is a very wide domain, and it encompasses various models, and it is a fusion of various models. And for this particular case, I will be little deep dive into process gas chromatographs that are being used for our polymerization reactors. So this is my agenda, and I will go step by step by explaining gas phase polymerization reactor. Then I will talk about little bit about reactor control philosophy. Then how the process gas chromatography is used for this reactor, and then I will deep dive into the digital twin and digital twin modeling concept. Then I will model a digital twin for this particular gas chromatograph, and then finally the impact of the digital twin. So any gas phase polymerization reactor, whether it is a polyethylene reactor or whether it is a polypropylene reactor, looks similar to this. and it is a continuous reactor. Gas phase based monomer will fed to the reactor, and solid polymer will be drawn out of the reactor, and it is very highly sensitive to the feed fluctuations and feed impurities. And common licenses are Universal Technologies and Dow Chemicals, SABIC. So the particular reactor I will be talking about is Univation's licensed. So this is the brief reactor control philosophy. So the temperature of the reactor, since polymerization reaction is an exothermic reaction, so temperature obviously it will be generating some heat. So the temperature control will be done using the heat exchanger I have mentioned in the photograph. And similarly, the rate of the reaction will be controlled by controlling the feed flow of the catalyst to the reactor. And similarly, the reactants flow will be controlled using the partial pressure inside the reactor. And here the gas chromatograph plays an important part, because how we will know which type of components are present inside the reactor, but what is the mole percentage of the particular components, then only you will be able to control the partial pressure of the components. So we will be measuring the partial pressure of the components using gas chromatograph. So this is the overview diagram for the reactor control philosophy. Or gas chromatograph is measuring, this is a fast loop gas chromatograph, it is measuring a mole percentage inside the reactor loop, and then it is feeding the mole percentage value to the partial pressure calculation block. Then the partial pressure calculation block is feeding the set points to the different feeds of the reactors, ethylene common or feed and hydrogen feed. So a brief about the gas chromatography. The gas chromatography is basically, it is having two phases, stationary phases and moving phases, and it is used to separate the mixture of gases to the separate components, and then we will measure the separate components, and then we'll know what type which components have how much mole percentage inside the reactor. Since it is a very sophisticated equipment and very sensitive to the environmental conditions like temperature, the oven is continuously maintained at a constant temperature, and the carrier gas pressure is also very important, and slight disturbance inside the carrier gas pressure as well as the oven temperature will produce erroneous readings. So this is how it is, the gas chromatograph is measuring the composition values and feeding to the dishes. As digital TV, you all in previous sessions it is already well explained. So I will just little more talk about the digital twin modeling. So we can model the digital twin by using three models. One is first principle based model, that is NSYS, using NSYS, SPEN and heat mass transfer equations. You can model a particular digital twin, but the advantage is that it is a high fidelity simulation, and the disadvantages are that it requires high computational. It is computationally complex. The next one is data driven model. It doesn't require any high computations. You once train the model, then you infer the value by feeding the inputs. I have also shown an example for instantaneous fuel consumption of the particular vehicle. Next, hybrid modeling. Hybrid modeling is basically fusion of two. We will fuse two modeling together, and we will minimize the composite loss to make a hybrid model. Basically, we are using physics informed neural networks to build these kind of models. So I will be more focused toward data driven modeling, that is I will be more focusing on deep neural networks, and this is particularly the model development process. You just collect the data from the historians, then you do the data preparation, then you do the model training on the data, then you evaluate the model, how the model is performing, then you repeat the process, and this goes on until you find it satisfying that the model is performing well. So this was my data for the model development, deep neural based model development for this particular gas chromatograph. I selected all the parameters. 8 month of reactor running parameters were selected. Total 23 parameters were there. Then I performed some basic data pre-processing, data normalization, outlier removal, data filtering using correlation. So these were the model inputs, and mole percentage I already talked about was the model output. So this is basic outlier removal. What actually the outlier removal is? Outlier removal is basically you are removing the data that is lying outside 3 sigma deviation of a particular data set. So I used 6 different methods to remove the outliers, and the encircled one was the performing better for my data set. Then I move towards data filtration. I will only select the data that is more relevant to the model, and I will discard the rest. So supposedly for the ethylene prediction, my nitrogen feed and common number feed and the data I marked with the red is irrelevant because it is showing zero correlation with my ethylene component. Similarly, we can do for all the outputs. Finally, model selection and model evaluation criteria. For basic machine learning models, I used highest R squared value and lowest root mean square error. And for deep learning based model, I used lowest training loss and validation loss and testing loss. So I will just more focused on deep neural networks because the basic machine learning models were performing better, but they require high data cleaning. So, and deep learning model were performing more better for this particular problem. So I will just move more focus on deep neural networks. So I trained a model for particular data, and this was the trailing and validation loss for this particular model. So ideal case, this closely resembles to ideal case or loss. My loss is converging to almost 0. So it means that model is performing good on the training data set. So these were some predictions made by the model. So ethylene that model predicted versus the actual ethylene reading. Similarly for the hydrogen, and then for the butene, because these 3 are critical. Use S2 by hydrocarbon ratio and common number by ethylene ratio are more critical for your any polymerization reactor, because they determine 2 polymer properties. S2 by C2 determines melt index, and common number divided by ethylene determines the density of a particular polymer product. So this was the comprehensive, I can call it as a digital twin architecture, because I'm predicting each and every mole percentage by using the 10 inputs, and each mole percentage prediction is using its own model. So this was like a representational view of that. So since this particular plant is not having proper IT/OT convergence, so I was using single machine that was also sitting on the L2 network. So this was the architectural view of that. So this is the final picture. How I can see my digital twin based model that is on the PID. So as we have seen earlier, PGC was also there, but if PGC is having breakdown and you're not able to calculate the mole percent composition of the reactor, then we can rely on the predictions made by digital twin that we have developed using the deep neural networks. So what were the major impact that it has created? So my reactor control has improved, because earlier I was having major PGC breakdowns. PGC was not responding to not properly responding, and it was giving erroneous readings. So because of those erroneous readings, my reaction got disturbed, and it was once the reaction has disturbed, it will produce out of spec product. So that was also resolved. And meanwhile, if I am having a steady state reactor operation, then I can do my maintenance on my PGC. So my mean time to failure for the PGC has also increased. and of course we have minimized the off-spec production for this particular reactor. So this curve shows the 6-month data for production quality for this particular reactor. The bar graph indicates prime grade product that is coming out of this reactor, and the line indicates the off-spec production that we had. So as we can see, the line line has a downward slope, and the bar is increasing. So we have managed to maintain, we have managed to increase the prime grade production by 5%. So I think I will not stop here. This is the way forward. I am developing PINN based model for this particular PGC. I will try to incorporate these reaction kinematics into this the data that I already have, and try to develop this based on PINNs that I'm currently working on. These were the open source technology that I used for this project. That's all from my side. Thank you.
So thank you, Mr. Ashok from GAIL, and he highlighted certain aspects of his work at GAIL with respect to process gas chromatograph, and we saw some of those mathematical equations, terminologies which he is using, and that's wonderful. And I'm sure GAIL is benefiting from those work that he is investing time and energies on. So my next presentation is from Reliance. I welcome Mr. Satyanarayan Arunachalam, who is Vice President Technical with more than 3 decades of experience working in this space. He will speak about driving value maximization with process digital twins and data analytics. Welcome, Mr. Satya.
Thank you, Chair. For the intro. Very good afternoon to you all. Yesterday is a history, tomorrow is a mystery, and today is an opportunity. How to leverage historical data to create sustainable success with today's latest digital technologies are the challenges for all of us. How to get the benefits from using these digital twins and data analytics, we will see one by one. Here I would like to acknowledge our colleagues for making these presentations. Mr. Jesse from our technology, Mr. Vikas, Mr. Kishore, and Mr. Narendra from our process automation department, and Mr. N.C. Chakravarti and Akhilesh Kumar from our smart manufacturing team. This is our corporate disclaimer slide. The scope of this presentation is purely for knowledge sharing purposes. Reliance is a Fortune 500 company with India's largest and most valuable company, having 240 plus billion market capitalization and 100 billion plus revenue and 20 billion plus US dollar as EBITDA. We have significantly moved from B2B to B2C in last 10 years and established market leading platforms in telecom, retail, financial and media. We are having assets of world class with global scale, and we have pioneered in vertical integration and conceived oil to chemicals well ahead of the industry. Reliance Jamnagar, a world largest hydrocarbon manufacturing complex having ultra 2 large refineries, petcoke gasifications and refinery off-gas based ethylene cracker unit and its derivatives, is always front runner in adopting latest technologies. We are in the process of making Jamnagar site as a future ready smart site by integrating and collaborating manufacturing execution systems that will respond in real time to the changes in the plant, site, supply chain, and customer needs. We are having unified digital platform to by integrating all the domain functionalities with appropriate interfaces. It will unfold our productivity by simplifying the process and automating digital tasks and eliminating the digital breaks, as well as to have the seamless communication across the stakeholders. The enablers what we are envisaging are digital twins, data analytics, and automated workflows, digital workflows, and smart cameras, smart wearables, and video analytics, as well as interactive dashboard, along with emerging technologies, whatever it is coming on our way. These digital modules will help improve our performances in safety, reliability, and productivity, along with profitability. Digital transformations. Digitization and digitalization are the precursors for the digital transformation journey. Having technology alone will not lead us to have the digital transformation, because digital transformation is the collaboration of people, technology, process, and data. Having right sensors for giving the right inputs to the right data analytics model will give you the right insight for the right people to take the action in the field to improve the operational excellence. The digital twin. The term digital twin is unanimously used in all the fields of the industries. People have different understanding for the word based on their perspective. For a continuous manufacturing process industries like Reliance, digital twin is a digital replica of all the process operations in the process unit in the form of model to mimic actual performance and operations. For mimicking that actual performance and operations, multiple models are required to be built and deployed. In that, first and foremost is the process models. They are heart of digital twin. They are based on either first principle or hybrid. It always gives the better insight of what is happening in the real time. Next one is data analytics. Data analytics model are based on self-learning AI and ML models, giving you the yearly event detections, whether my unit is or equipment is running as per the design, or whether it is having any deviations or not, whether it is operating in the good operating zone or not, everything we can get it from data analytics model. And third one is equally important to both data analytics model and process model is the interactive dashboard, because it integrates all the value added and high quality data from these above two models for the better visualization and to have the faster decision making. Now we will see what are the benefits we will be having with this digital twin. Process digital twins will facilitate to have the new way of working by providing real-time optimization for improving our operational excellences. Also, it will bring out the hidden opportunities. Process digital twin will give the precise view of our operational capabilities and constraints in real time. Monitoring of key performance indicators of process, equipments, and advanced process control will be able to address the gap then and there. Even it will be useful for a catalyst changeover. Suppose during end of run, we will be having multiple problems like increase in the utilities, and at the same time there will be the deterioration of the process yield pattern, and there will be the penalty for getting the new catalyst and getting used for by preponing the catalyst changeover. Which is best, which is optimum. All those things we can get it from these digital twin applications. At the same time, if you are having the reliability model, it will also help us to understand the corrosion problems and erosion problems. We can solve them. Similarly, not only in real time, but if you are having the faithful real time model in offline, you can do so many what if analysis. For having the same infrastructure, what are the alternative feedstocks you can process to get more value added products. Similarly, you can also see what are the operational changes I have to do to get much more better superior yield pattern or to reduce the energy conservations. What are the bottlenecks, how to address, and during this revamp also you can see the real constraints on the each equipment wise and what are the scope of new revamp case studies. All those things we can get it from these digital twin models. Now let us see with one small example. Today we have seen two examples from our fellow speakers. One is our reforming unit, another one is the real-time gas chromatograph, how it is used in their particular perspective business. Now this is the common example so that we can see what are the other benefits envisaged by them during their presentations. See, distillation column is one of the most widely used process operations, unit operation in the process industry. For any industry, for a given feedstock, for getting the right product with minimum energy consumptions is the real challenge in the energy consumption point of view. In a distillation column, a mixture of hydrocarbons are getting separated based on their boiling point. Here, the objective is to meet the product yield quality and product yield pattern with minimum reboiling duty and overhead condensing duty. So here we may be having advanced process control system to optimize the reboiling duty as well as the condensing duty by having certain range for each variables. But exactly what is the minimum reflux ratio to be given for getting the right product may be missing for most of the distillation cases. Here comes the handy for having real-time digital twin applications. The model, generic model available for distillation column will be customized based on the unit configurations and it will be fine-tuned based on the operating parameters as well as the lab data. Once the model is validated, we can put it online so that it will start giving the real-time insights of the column operations. It will give the what is the minimum reflux ratio so that you will be getting the right quantity of product with right spec. But other than that, along with that, it will also giving many insights. For example, it will also giving you the stage-wise loading of the column. Like sometimes some of the loading stages will be nearing the constraints. Some of them will be having the cushion margin. So whenever you are going for the next revamp or any process improvement, the respective engineers can address those issues for making the further improvement in the capacity. At the same time, we can also get the composition of all the streams coming out of the column. For example, if you are having the net gas compressors at the overhead of this distillation column, you can have the real-time feed composition to the compressor so that your calculation of polytrophic efficiency or volumetric efficiency will be more accurate. That will be used for addressing the problem associated with the compressors. Similarly, if you are having the downstream unit where you need the quality of this upstream stream, there you will be getting the full insights so that you can optimize the downstream processing unit also. That is how having the digital twin not only serving the purpose of either planning or particular process unit, it is also serving as the global umbrella for both downstream and process unit as well as the equipments. Now we will come to the data analytics. Over the period, the application of process data analytics has improved significantly thanks to the next generations IT applications like IIoT or self-learning, AI and ML technologies or big data analytics. So we have evolved from descriptive data analytics where the focus is mainly on what has happened. Then we have evolved into diagnostic analytics where the focus is why it has happened. Now we are in the process of or in the phase of predictive analytics, where the focus is what will happen. Now we are approaching the final stage as the prescriptive analytics, where the focus is what should happen to improve the operational excellence for my process unit. Here there are two classifications. One is decision aid, another one is the decision automation. Here the decision aid is the open loop. It will give the recommendations for the field team to act upon to get the desired results. But in decision automations, it will also trigger what are the action points in the field they will be doing that it will try to activate in the DCS itself. Those kind of decision is called decision automation based prescriptive analytics. Here our endeavor is to make our prescriptive analytics with decision automation wherever it is possible. Now we'll come to the live example where we have utilized this data analytics to improve our operational excellence. See, we are having world largest petcoke gasification complex at our Jamnagar. Here we are having a significant problem in improving the run length of our key equipments. Since gasifier is the complex process unit, building the first principle models and getting the results to get the deviations, it is extremely difficult. So here we started using data analytics to get the better insights. So the business case is that run length to improving the run length of the key equipments. So we have collected the data corresponding to each run length and clustered according to their run length period. Then we started analyzing what is causing the deviations among each operating zone. For that we are using the data analytics technologies. And finally, we were able to identify what are the parameters, not only parameters, and what is their operating range. If you are able to bring back to the recommended operating range, we will be able to increase the run length of those equipment. So finally, once the model is validated, we have converted to the language of operation team so that they will be in the better position to take the corrective actions if there is a deviation in the operating parameters for which is affecting the run length of the particular equipment. And over the period, we have evolved and improved the model and fine-tuned further so that currently our gasifier is running at great success. Around hundreds of models we have built only for our gasifier units. See, with that, what I am trying to tell you is that having digital twins and data analytics will definitely improve our operational excellence. At the same time, having technology alone will not make that digital transformation journey. It is the collaborative efforts of people, work process, and technology and data analytics together we have to improve the system. These both digital twins and data analytics are the result of multiple teams working across the Reliance India as a single team. And we are having the clear strategy roadmap for completing and implementing these digital twins across our process units in a couple of years. I am taking this opportunity to thank IEW 2025 team for giving me this opportunity to sharing our journey. Thank you. Thank you very much.
So thank you, respected speakers. We had diverse views and thoughts from Indian Oil, GAIL, Reliance and Siemens. Thank you once again to the speakers who shared their views and experiences. I'm sure it was an enlightening. Thank you audience for patient hearing. With this we come to the close of this session. Thank you once again.